is a pulley of mass M, radius R. A pulley of mass M, radius R. Pulley of mass M, radius R can rotate freely about a smooth horizontal axis through its center. A light inextinguishable string passes over the pulley and a masses M1 and M2, and the masses M1 and M2 are attached to the two ends. Okay, so it's a pulley, and around this pulley there's a string passing over it. In this side there's a mass M1. There's a mass M1 attached to it. Okay, and let's say M2, and in the other side there's a mass M1 attached to it. Okay, so this is the diagram. So can you understand that this question perfectly matches with the topic? What is the topic? Combination of linear and rotational motions. Let's see whether linear motions and rotational motions are combined here. Let's check what happens. As they say, M2 is the greater mass. As they say, M2 is the greater mass. Let's mark the weight. M2 is the greater mass. So it's having a higher weight. So what will happen? M2 will move down. M2 will move down. When M2 moves down, what happens? For M2 to move down, string has to come down like this. When the string is coming down like this, it has to pass the pulley like this. It has to pass the pulley like this. To do that, from the other side, string has to move up. String has to move up. And from there, what will happen to M1? Let's mark its weight, M1G. And what will happen to M1G? It will move up. So M2 is the higher weight. So M2G is the higher weight. So the mass M2 is moving down. For that, string has to move down from right side. To that, string has to pass over the pulley in a clockwise manner, bringing the M1 up. So M1 and M2 are in linear motion. While M1 and M2 are in linear motion, what happens to the pulley? When a string passes over the pulley, what happens? Automatically, pulley also gets a rotation. String is passing over the pulley, touching it. So what happens? Pulley will also get the rotation. Okay, so the topic is correct. Combination of rotational and linear motions. Pulley is in a rotational motion due to the string passing over it in a clockwise manner here, and the two weights are in a linear motion, one downwards, other upward. Okay, so let's mark the forces. Weights were marked M2G, then the tension of the string. How to mark the tension of the string? Tension of the string attracts the contact point towards the string itself. Tension of the string attracts the connected point towards the string itself, T. And here what happened? The tension of the string attracts the place where it is touching a pulley towards the string itself, T. Here, the contacting point is attracted by the tension of the string towards the string itself. And the touched point with the pulley is attracted towards the center of the string by the string. That is how we mark the tension. But there's a small problem. This was the final question I discussed last week, and I'm rediscussing it while you are doing the other questions. So what was the problem here? Am I correct here? Is the forces correct? No, there's a slight mistake. In both sides, tensions are not equal. Why? Sir, when we were doing F equal MA, we can remember that we solved the same problem. When we were doing F equals MA, sir, we solved the same problem. M1G, can't you remember, sir? Here it's M2G, here it's M1G, then the tensions T, T, other side, tensions, T. Sir, so what's the difference? We did it like this. Tensions were equal throughout the string. Can't you remember? No, Puta, I can remember, but there's a problem. When we were doing F equals MA, at that moment, we were not taught about the rotational motion. So what we did? We assumed that the tensions are equal in both sides. Why? See what happens when the tensions are equal. Learn carefully. Learn the theory correctly. See what happens when the tensions are equal in both sides. Here, from the center, the perpendicular distance is R. Okay, so what is the moment here? The force is T acting on the pulley, T into R, moment is TR. And what happens in the other side? You know how to mark the tension close to a pulley. The string attracts the connected point of the pulley towards itself using the tension. So this is the tension. This is the normal distance from the center, R. Moment, force into distance from the center, T into R, so moment is TR. So if the tensions in both sides are equal, what happens? To right side, clockwise side, moment is TR, and for the anti-clockwise side, moment is T into R, moments are equal. When moments are equal, object doesn't rotate. When moments are equal, object will not rotate to any side. As we were doing F equals MA, when we were doing F equals MA those days, we don't know about the rotational motion. So we need the method to avoid pulley's rotation. We need to neglect pulley's rotation. So what we did? We assumed that the tensions are equal in both sides. If the tensions are equal in both sides, what happened? The moments will cancel out. When the moments cancel out, what happened? The rotation is not considered. Rotation need not to be considered. Moments are cancelling the rotation. So what we did in F equals MA, not considering the pulley, it's not rotating. Just the string passes over the pulley, slipping over it. Just the string passes over the pulley, just slipping over it. So that was the way we did F equals MA lesson, as we were not aware of the rotational motion those days. But now we are aware of the rotational motions in the real world. When two masses are attached through a string, passing over a pulley, when these masses move in the real world, we know that the pulley also rotates. When the string passes over it, the pulley also rotates. It's general knowledge. So we need to match that real case scenario with our theory. So what we need to do? We can't keep the tensions equal. We can't keep the tensions equal. If tensions kept equal, what will happen? They will cancel out the moments and the rotation will automatically stop. But the real case is the rotation is present. So let's differentiate the tensions. Okay. Here it's T1, here it's T1, and here it's T2. Okay. Now, you know that in rotational motion, you can't keep the tensions equal. In rotational motion, you can't keep the tensions equal in both sides. In order to maintain the rotation of the pulley, tensions should be not equal. So T1 here, T2 there. Okay. Then what we did? The last week final question, what we did? Then for the linear parts, we applied F equals MA. Okay, for the M2, I'm applying F equals MA. Here, M2G minus T1, M2G minus T1, M2G minus T1, mass M2, acceleration A. It's moving down with an acceleration A. M2G minus T1, M2A. Okay, now listen carefully again. When the acceleration is A, for the M2 to move down with an acceleration A, the string has to move down with the acceleration A. String has to move down with the acceleration A. For that, string has to get released. For that, string has to get released with the acceleration a. If the string get released with an acceleration a from the tangent of the pulley, if the string get released with the acceleration a, then only it will drop down with the acceleration a. Then only M2 will gain the acceleration a. So the tangential acceleration here is a. So for the string to be dropped down to come out from a tangential acceleration a, in order to drop down with the acceleration a from the other side, it has to move up with the acceleration a. It has to move up with the acceleration a. Then only it get that tangential acceleration matched. Then only it will get that tangential acceleration matched. So the acceleration here is also a, and moving upward with the a, tangentially releasing the string with the acceleration a and dropping down with the acceleration a. So it's a common acceleration a. And when the pulley in its tangent, when it's having acceleration a, the rotational acceleration will be alpha, where a is equal to r alpha. You know from the previous parts, when a tangential acceleration is present known as a, if the radius is r, the rotational acceleration alpha, a equals r alpha. A equals r alpha. Rotating method, in a rotation, when the angular velocity changes, it gives birth to a rotational acceleration, angular acceleration. It's alpha. It's relating with the tangential acceleration, a equals r alpha. It's also present. Okay. Applied F equals m2, m2g minus t1, m2g minus t1, m2a moving downward. Then applied F equals ma upward. Then applied F equals ma upward for the m1. Here from this side, m1 moves up. T2 minus m1g. Here F means the resultant force. In F equals ma, F means the resultant force. What is the resultant force upward? T2 minus m1g. T2 minus m1g. In F equals ma equation, what is F? The resultant force to the dedicated direction. So here m2g minus t1, m2a. Here t2 minus m1g, m1a upward. Two equations. It's the second equation. This is the first equation. Okay, I think you are getting a perfect picture quality and perfect sound. Okay, so this is our home studio. Let's continue in this way and we will get using this method. Okay, now if there are any errors in sound or in the picture quality, keep us acknowledged, keep us informed. Okay, so and the other thing, now this M2 is moving down while M1 is moving up. So the stream passes over the pulley, giving a rotation to the pulley. Okay, for the rotational cases, I'm not going to apply F equals ma. The equation is tau equals I alpha. The equation is tau equals I alpha. Tau equals I alpha. Can you remember? So what is tau? The moment that gives the rotation. What is the moment? Here to this side, the force is T1 with the perpendicular distance r, T1r. But it's not the resultant moment. Why? To this side you have T1 into r, but for the other side also you have an opponent, T2 into r. Can you understand that? Here when you consider the pulley, the string is passing like this. In this side it's T1, perpendicular distance is r, so the supporting moment is T1r. But T1r will not get the chance to fully govern the motion. That's the opponent. What happened? To this side you have r again and you have a T2. So for this side what happened? Force is T2, perpendicular distance r. T2r is also present. T1r will win as M2, M1 here, this M2. T2, here T2, T2r will win. Here T1, here T1r. Here it's, I have done a mistake. It's better to correct the symbols, no? Let's mark T2 here. Let's mark T2 here. And let's mark T1 here. I think you have already done in that way. as this is M2. As this is M2, let's mark T2 here, and here T1 will be better. So M2G minus T2, okay, it's matching then. M2G minus T2, M2A. This side, let's make T1. M1G minus T1, T1 minus M1G, T1 minus M1G, M1A, the second equation. Okay, this side 2's, M2 minus T2G, M2A downward. This side 1's, T1 minus M1G, M1A. And applying tau equals I alpha, this side you have T2 then. T2 times R is the moment that brings the rotation. But there's an opponent from the other tension, T1. T1R is in the opposite side. So what is the resultant tension towards the movement? T2R minus T1R. So isn't it? The resultant moment, T2 times R minus other side one, T1R. Okay, take it that way. Then the resultant moment is taken here, and IR. It's a pulley. It's a pulley, and pulley is considered as a disk. If especially not mentioned, pulley is taken as a disk. For a disk, moment of inertia, half mr square. Half mr square. You know, for the rotational bodies, when we apply tau equals I alpha, I, the moment of inertia, we can't use mass whether we are using for F equals ma. For the rotational bodies, instead of mass, moment of inertia is used. For disk, it's half mr square. And the rotational acceleration alpha should be used. What is alpha? A is equal to R alpha, where alpha is equal to A over R. A over R. So for alpha, it's A over R. What will happen? One R will cancel out here. The other R will cancel with this. So T2 minus T1 is equal to M over 2 into A. This is my third equation. Then what will I do? Then I will add all three equations. Then I will add 1, 2 and 3. When I am adding 1, 2 and 3, what will happen? What will happen? M2G minus T2. M2G minus T2 plus T1 minus M1G. T1 minus M1G plus T2 minus T1 gets equal to M2A plus M1A plus M over 2 times A. Then what will happen? Tensions cancel out. When I add the equations, what will happen? The tensions cancel out. So M2G minus M1G is equal to A times M2 plus M1 plus capital M over 2. From there you can subject the value A. From there you can subject the value A. Okay, from there you can subject the value A. Okay, now what is the value A then? What is the value A? Okay. G M2 minus M1, G M2 minus M1, G taken out, M2 minus M1, here M2 plus M1 plus capital M over 2 is the answer for the acceleration. It is the answer for the linear acceleration. When the string passes over the pulley, you have that acceleration tangentially, dropping down the mass in the right side and bringing the mass upward in the left side. Due to that tangential acceleration, due to that string passing over the pulley is rotating, having a rotational acceleration alpha. You know the equation, A is equal to R alpha. So alpha will be equal to A over R. So alpha, the answer alpha will be equal to 1 over R times A. 1 over R times A. G M2 minus M1 here m2 plus m1 m over 2. You can simplify it more. You can simplify it more, but I'm not going to simplify it more because it was the final question I did last week. So I'm not going to take more time on that. Now you get the idea. So what's the topic here? After the angular momentum, we did the conservation of angular momentum. Then we came to the topic combination of linear and rotational motion. Some parts rotating while some parts in the linear motion. These are the questions. Okay, continue with the other questions 85, 86 and 89. If we have finished, you can go to the 87th question too. You can go to the 87th question too. If you need the tute, you can keep me a WhatsApp message, then I will send it to you. If you need the tute, you can keep a WhatsApp message and I will send it to you. After, if there's a new student joining today, he or she can refer the PDF for the week and he has to send me the details. Then in the normal case, we are delivering the tute to the home via speed post. Okay, so now let's continue. Question number 86. Question number 86. No, it's 85. It's 85. As the next question, I had to do the question number 85. I had to do the question number 85. In question number 85, what happens? It's a small practice for the previous theory, previous method. Here, a pulley can rotate freely about a smooth horizontal axis through its center. A light inextensible string passes over the pulley, masses 0.2 and 0.25. Here the mass is 0.25, having a weight of 2.5 newtons. In the other side, mass is 0.2, having a weight of 2 newtons. And it's not a F equals ma question, it's a rotational motion question where you have to understand that the pulley rotates. For the pulley to rotate, the tension in the both sides should not be equal. Marking the tensions, here it's T2, and the other side, the tension is T1. Remember, tension always attracts the connected point towards the string itself. So, attracting it towards the string itself, and the tension always attracts the touched point of the pulley towards the string itself. So, it's like this here. Okay. And when this higher mass is moving down with an acceleration A, string has to drop down with the acceleration A in order to do that. So the tangentially, string has to be released with an acceleration A. For that, from the left side, the mass 2 Newton weight has to move up with an acceleration A. It's a common acceleration A. Due to that acceleration, pulley will, due to that string that passes over the pulley with the tangential acceleration, pulley will rotate with the angular acceleration alpha. Angular acceleration alpha. Okay. Now applying F equals ma downward for the 2.25 kg mass. In F equals ma equation, F is the resultant force, 2.5 minus T2. 2.5 minus T2, mass 0.25, acceleration A. And applying F equals ma upward for the 0.2 kg mass, and there the force is upward force. So it's T1 minus 2. It's T1 minus 2 is equal to 0.2 times acceleration A, the common acceleration that governs the linear part. Okay, and applying tau equals I alpha for the disc or the pulley that rotates, tau is the resultant torque. In this case, pulley is rotating. Previously, when F equals ma, pulley does not rotate. In order to achieve that, tensions were assumed to be equal in both sides, cancelling the moments to the opposite side. But here it doesn't happen. In the actual case scenario, the pulley rotates. So how to manage it? The perpendicular distance from the center is R, force T2. T2R will be the helping moment, force into perpendicular distance to pulley's rotation. But there's opponent, T1 times R. T1 times R is in the opposite way, so you have to subtract that. T1R is equal to the moment of inertia. Is the moment of inertia given? Is the moment of inertia given? Okay, it's the moment of inertia given. No, it's not given and it's asked. It's asked. Okay, What is alpha? Moment of inertia is not given, it's asked. What is alpha? Angular acceleration that the pulley achieves when the tangential acceleration is governing the linear part. Acceleration that's in the tangent A relates with the angular acceleration A equals R alpha, where alpha is equal to A over R. A over R. So T2 minus T1, dividing this R to other side, A over R square. T2 minus T1, I don't know the I value, moment of inertia to be used. It's the property that we are using instead of mass in a rotational motion, moment of inertia. Acceleration is given. The value of the acceleration is 0.3. 0.3, you have to divide by the square of the radius. What's the radius? Okay, radius is also not given. It's R square. It's R square. Okay, then okay, let's continue. Then what happened? R is also not given, so I kept it. I'm subjecting T2 minus T1 from the left side to be cancelled out with the above parts. And for this R, I took it to the right side, the bottom. Acceleration 0.3, R square is here. Okay. Now I'm adding the equations. 2.5. Now I'm adding the equations. 2.5 minus T2 plus T1 minus T2, T1 minus 2 plus T2 minus T1. In the right side, what I have? In the right side, 0.25a, 0.2a, I times 0.3 over R square. I'm adding them. When I add the left side, minus T2 will cancel off with the plus T2. Plus T1 will cancel off with the minus T1, leaving 2.5 minus 2 will be the left side. The remainings of the left side will be 2.5 minus 2 when I add all the three equations I get. 2 from linear motion, 1 from rotational motion. In the right side, 0.25, 0.2, 0.45a. 0.45a and again, I times 0.3 over R square. What is this 0.3? Acceleration is given. 2.5 minus 2 is 0.5 and 0.45 into acceleration. Acceleration was given and it was substituted as 0.3 here. I substitute the acceleration 0.3. So why can't I substitute it for the other places where acceleration appears? 0.45 into 0.3. Acceleration is 0.3. It's already substituted to the other place also. 0.3 over R square. Okay. 0.5 is equal to 0.45 into the acceleration. As acceleration is 0.3, 0.45 times 0.3. 0.135. 0.135. I, moment of inertia, 0.3 R square. 0.5 I'm subtracting 0.135 by 0.5, 0.365. I 0.3 over r square. It's a pulley is considered as a disk. Pulley is considered as a disk. 0.365. I moment of inertia half mr square. Half mr square. Moment of inertia half mr square. Pulley is considered as a disk. Half mr square. 0.3 and you have r square here. Unwanted r square will cancel out, leaving the m value here. Cross multiplications 0.365 multiplied by 2 divided by 0.3. Divided by 0.3 will be the answer for m. 0.365 multiplied by 2 divided by 0.3. 2.43. 2.43 kilograms. Mass is equal to 2.43 kilograms. Okay. Then move to question number 86. Then move to question number 86. I think you can make a very good use of this class. Huh? It's Monday evening. You are not tired yet by the schoolwork. Schoolwork is to be started. That means it's just Monday. Okay? And the tiredness is gathering when the days of the week are passing. Fridays, Thursdays, they are somewhat tired. Now it's just the Monday. And it's the camera. I'm looking at the camera and I'm teaching only for you. As in, it's just online class, a separate online class. So take the full use of it. Take the full use of it. This is the nature. I'm teaching the theory to the fullest. I'm teaching the theory to the fullest, to the deepest level. Okay, I'm teaching the theory to the deepest level, and we are solving a lot of questions. We are solving a lot of questions. So this will be a good practice for you. Take the full use of it. Okay, now let's go to question number 86. Let's go to question number 86. A light string is wound round a drum of radius r, which can rotate about its axis. A light string is wound round a drum. So, do you know what is a drum? If someone needs a tube, yes, wait, Puta, there's another message. So can I? Yes, Puta, I'll send. Okay. Send the tube. Okay. Now, what is a drum? It is not a pulley. It's a kind of a cylinder thing. It's a kind of a cylinder. In a pulley, you can't so many rounds of the string around it. But in a drum, that's the difference. Here, see, you can keep so many rounds of the string around it. It's a long disc. It's a cylinder. Know these things, huh? So at the final moment, when the final round is passing, it's the same way, the same behavior as a disc. Here, in the final round, it comes like this. Draw it symmetrically. For the student who asked the tute. I have sent it now. Okay, so it's like this. And here a mass is attached. And from the axis is also there. You have to consider that also. Like this. This is the axis. Okay, so this is the case. Now, what they ask, a light string is wound round a drum of radius r, so the radius is r. So the radius is r. Radius is r. And a mass is attached to the end of the string and allowed to fall. The mass is m, giving a weight of mg. Giving a weight of mg. Okay. Then the moment of inertia of the drum about its axis is I. When the rotation goes on, the moment of inertia of the drum is I. If the mass falls through a distance x, if the mass falls through a distance x, if the mass is falling down from a distance x, from a distance x, if the mass is falling down from a distance x, from a distance x, the velocity it gains is v. The velocity it gains is equal to v. Okay, so you have to prove something. You have to prove something. Okay, how can you do that now? What is the way to do that? Question number 85, 86, 89, 87. Now, this is my idea. First of all, I have to mark the weights. Here it's m2g. The weight is m2g. And the tension here, T1, let's say T. And from the other side, when it touches the pulley, when a string touches the pulley, it attracts the connected point of the pulley towards the string itself, giving a tension like a tension T here. It's T. Okay. Due to this tension, what will happen? This tension is having a perpendicular distance r with the cylinder, giving a rotational acceleration alpha. When the tension is, you know, the tension is in the circumference, it's a tangential force having a perpendicular distance of r from the center, creating a moment, rotation T r. and due to the TR, this thing will rotate with the angular acceleration alpha while the mass m moves down with the acceleration a. And as the mass m moves down with an acceleration a, the string has to come down with the acceleration a, supplying the mass acceleration a. String will also move down with the acceleration a. So tangentially, string has to be released with the acceleration a. Then only it will drop down with the acceleration a, giving the mass acceleration value a. Okay, the radius is r. Radius is r. So famous A equals R alpha equation is also present. Tangential acceleration, radius times angular acceleration. It's also present. Okay, applying F equals ma. Applying F equals ma for the mass m. F is the resultant force to the considered direction downward. Mg minus T. Mg minus T. Mg minus T is equal to ma. Mg minus T is equal to ma, moving down. Okay. Now I'm applying tau equals I alpha. I'm applying tau equals I alpha for the drum. For the drum, I know according to my picture, the drum is having a clockwise rotational motion. What is the moment that rotates the drum? Tension times R. Tension times R will be the moment that rotates the drum. The other side of the tension, T into R will be the moment. TR, I, alpha. Okay. Angular acceleration alpha relates the tangential A equals R alpha, where alpha is equal to A over R. Alpha is equal to A over R. So T is equal to, dividing this R to the other side, I, A over R square. The second equation. Okay. Now I have two equations. Going to add them. 1 plus 2. Mg minus T plus T. Mg minus T plus T. From the other side, Ma plus Ia over R square. T will cancel out. Mg is equal to A taken outside, M plus I over R square. By looking at the answer, I can see a MR square value. In the answer, I can see a MR square value. So thought of dividing all the parts from M. Thought of dividing all the parts from M. Mg divided by M, and acceleration here, M plus I over R square divided by M. Thought of dividing all the parts by M. Okay. Then what will happen? Wait. Sort of dividing all the parts by A. So I'll write in the other place. I'm dividing all the parts by M here. See? Dividing all the parts by M. Then what will happen? Mg over M, the G value. Acceleration, and this M divided by M, 1. And I over R square divided by M, I over MR square. I over MR square. Okay. Now I have acceleration value. So the acceleration is equal to A G over 1 plus I over MR square. I over MR square. Okay, divided all the parts by M, then Mg over M became G, and A remaining, and M plus I over R square divided by M, M over M1, I over R square divided by M, I over MR square. Then go to the acceleration. As the final target, I am applying V square is equal to U square plus 2as downward. If the acceleration is found, no need to worry from there. I am applying v square is equal to u square plus 2s. After a distance x, it has gained a velocity v square. After the distance x, it has gained a velocity v square. Initial velocity 0. The system starts from rest. Initial velocity 0. After distance x, it got a velocity v square. 0 square 2. Acceleration is known, g over 1 plus I over mr square. The acceleration value is the complex value. We can substitute it. S, the displacement. The mass moves down from a displacement x in order to get v. S is equal to x. So what happened? V is equal to root 2gx 1 plus I over mr square. Okay. Okay, in the way. Now, what is the common thing? What is the common thing that we saw in all these questions? What is the common factor? The common factor is that when you consider the system, some parts are having a linear motion while other parts are having a rotational motion. So this is the case. Okay, so the topic, combination of linear and rotational motions, it's done. Okay, let's come to the final topic of the rotational motion lesson. Let's come to the final topic of the rotational motion lesson. Okay. Okay. As I'm what's the time that we are going to the interval? Okay, let's move to the interval around 9. Nah? At 9 p.m., let's take an interval. Okay, so it's the final topic of rotational motion. Okay, children. So write it. Rolling motion. Rolling motion. Rolling motion. What is a rolling motion? How it is connected to the rotational motion? What are the equal factors? What are the different factors? Let's talk about the theory. A rolling motion. What do you mean by roll? Take a fan, it's not rolling. It's rotating around the center. Take a fan, the blades, they are not rolling. They are rotating around their center. Take a vehicle wheel. When the vehicle is traveling, the vehicle wheel rotates around itself while moving from one place to other. That's rolling. Object has to rotate while moving from one place to other. Not the fan, but the vehicle wheels when the vehicle is moving. I think you got it. Okay, write a small sentence. Object has to rotate while having a linear motion. Object has to rotate while having a linear motion. Object has to rotate while having a linear motion in order to fulfill a rolling motion. In order to fulfill a rolling motion. Okay. So don't write. So if we need to understand the rolling motion, the best way is to combine the rotational motion and linear motion. Why? In a rolling, when the vehicle wheel travels from one place to other, it rotates around itself while there's a linear displacement from the first place to the second place where the vehicle went. Okay, so let's draw the velocity components in a rotation and the velocity components in a linear motion separately, and then we will add them. Then we can see what's the case of a rolling motion. To see the velocity profile of a rolling motion, let's vector-wise add velocity components in the rotational motion to the velocity components in a linear type motion. See, like this. When an object is rotating around itself, it has tangential velocities like this. Okay, while having a angular velocity omega like this. The rotation is that tangential velocities while having angular velocity. Rotation. If an object is, shall I draw it as a larger diagram? When a wheel is rotating, when a wheel is rolling, it has the rotation and the linear motion both. If it is a rotational part, I am considering the rotational part. In the rotational part, to rotate, angular velocity is essential, omega. And due to the angular velocity, tangential velocities will be produced. V. And tell me another thing. For the rotation, angular velocity is essential. Tangential velocities are there as marked. Okay. The next thing, when rotation is going on, the tangential velocities are present, as we have known from the initial parts of the lesson. When a rotation continues, there are tangential velocities both. They are from the first part of the lesson. And the next thing, angular velocity is also present. And in a rotation, the exact center is not having a velocity. All the other particles move around it. Look at the center of your fan in your room. The exact center, it's not in a motion. All the other particles move around it. So the center doesn't have a velocity. In a rotation, the exact center doesn't have a velocity. All the particles are rotating around with a omega value, producing tangential velocities too. So this is the rotational part. Meantime, let's add the linear components. Let's add the linear components. If an object is moving linearly, what can you say? If an object is moving linearly, what can you say? All the molecules in it will have the same velocity towards the motion. If you are moving in your car, time to time, do you need to worry about the side glass? No, it's coming with you. If you are moving in the car, time to time, do you need to worry about the dicky? No, it's there, it's coming with you. If it's a linear motion, all the parts have the same velocity towards the motion. Okay, so the topmost point will also have V. The center will also have V. Right side corner will also have V. The bottom will also have V. The leftmost part will also have V. If an object is in a linear motion, all the parts have the same velocity towards the motion. That's why you don't worry about the gadgets in your car while you are driving. They will also come with you in the same speed. It's always as a set, a system moving with the same velocity. That's the behavior of a linear motion. And earlier I have drawn the behavior of a rotational motion. And the rolling means the addition of linear and rotational components. Why? In a rolling, it rotates while having the linear motion. So let's add them. So in a rolling, what will happen? You have to take the addition of all the parts. For rolling, you have to take the addition of all these velocity components. And fascinating things will happen. See what happens? When you add this v and this v, the topmost point becomes 2v. And in the center, it doesn't have a velocity. The center of the fan doesn't have a velocity, 0. But in the linear motion, all the parts moving with v, so the center will gain 0 plus v. From the rotation, no velocity for the center. But from the linear part, there's a v. 0 plus v means v. The center will get a value v. While the topmost part, from the tangent, it's v. And from the linear motion, it's v. It's 2v. What will happen to the right side corner? From the linear motion, a v like this. And from the tangential motion, a v like this. Okay? And for the leftmost part, from the linear motion, a v like this. From the tangential motion, from the rotation, a v like this. And the most fascinating point, the bottommost point, what will happen to it? The bottommost point. From the rotation, when the rotation happens like this, the tangential velocity is acting to the left side of the picture. You can see when the omega is like this, the tangential velocity is to the left side. And if the while get the imagine what's happened in the vehicle wheel. It rotates like this and it move forward. Imagine what happens in the vehicle wheel. It rotates like this when it is moving forward. So in the rotation, tangential velocity is to the left side, while the tangential velocity is to the left side. It rotates like this while the vehicle moves this way. So what happens? The linear velocity is to this side, v. And what will happen? These two v's will cancel out, resulting a 0 velocity for the bottommost point. It's a very fascinating thing. Okay? Then what else? From the vectors lesson, if you have v and v perpendicularly, you know the answer. Actually, it's root 2v, the real case. If you have v and v perpendicularly, actually it's root 2v. Here, v and v, it's 2v. 2v. Here, 2v's are cancelled and 0. Okay. In the center, from the rotation, you don't have a velocity to the center. From the linear, you have a v, so it's a single v value in the center. While rotating, it moves forward. So this omega, it's still there. This omega, it's still there. So this is the velocity profile of a rolling. It's relatively complex than normal rotation. Okay. Write down the sentence. The velocity profile of a rotation. The velocity profile of a rotation is the vector addition of the velocity profile of a rolling. Velocity profile of a rolling is the vector addition. Velocity profile of a rolling is the vector addition of the rotational motion part, vector addition of the rotational motion part and the linear motion part. Vector addition of the rotational motion part and the linear motion part. Okay, you can complete the picture. You can complete the picture. Always when you are doing physics, always imagine, while you are drawing this thing, imagine how a vehicle wheel moves. It rotates around the center while moving from one place to other. If something rotates, angular velocity is there, tangential velocities are there, center is having a zero linear velocity. If someone is moving from one place to other, all the body parts have the same linear velocity, the second case. In a rolling, while rotation, linearly move from one place to other. Have to add the vectors to get the velocity profile of a rolling. So what we did? So we took the vector addition. In the topmost point, it's 2v. Bottommost points, v's are cancelled to the opposite directions. In the left and right side corners, perpendicular v values, creating a final answer root 2v when two perpendicular vectors are there with the same value. Resultant is root 2 times the 1 time root 2 times v. And don't forget, still the wheel is rotating while moving. Angular velocity is also there. Okay, fill the picture. Okay. Now, when a rotation is mentioned, you have to know the velocity profile. Topmost point 2v, right and left side root 2v, bottommost point 0, center just 1v gain from the linear part as rotation does not add anything to the center. And again, the angular velocity is present, omega is present. This is the velocity profile. Okay. And here, when I was in university, they proved these equations, but for the A levels, you have the chance to take them without any proof. What's the equation? If you have done this in school, what's the equation? V equals R omega is available. Most of the children think this V equals R omega is the previous V equals R omega that we used in the beginning. No. Look at the board. When a normal rotation is carrying, the tangential velocity V is equal to radius times the angular velocity. V equals R omega. But here, it is not that V equals R omega. Can you remember? If it is just a rotation, tangential velocity, radius times angular velocity, V equals R omega. But remember, this is not that V equals R omega. In the tangent, you have 2V, root 2V, 0 and root 2V. In a rolling, the tangent is very complex. When we consider the velocities on the tangent, velocities on the circumference of a rolling body, they are very complex. In the top, it's 2V. In the bottom, it's 0. So how come V equals R omega be there? If the V is the tangential velocity, no. V will be the tangential velocity and R times omega, it is for just a rotation. It's just for rotation. The symbols look like same, but it's not the case. Here, this V equals R omega stands for V is the velocity of center. V is the velocity of center. You can write it with me. Velocity of center. You can write it with me. This V is the velocity of center. R is the radius. And this is the angular velocity. This is the angular velocity. Okay. So what's this V? It's not the tangential V. In the tangent, you don't have a V. Once it's 2V, sides it's root 2V, bottom it's 0. So no tangent with the value V. That V equals R omega. is for the pure rotational motions. Now it's not the case. The velocity in the center, V, velocity in the center is equal to radius times angular velocity omega. Note down it clearly. You will get, don't mess it with the previous one. Velocity in the center in a rolling is equal to r omega. When the object is moving from one place to other, while rotation, it's rolling. In a rolling, the velocity in the center is equal to r times angular. Okay, it's not the previous equation, even though it has the same symbols. And the next important point, how to write the kinetic energy of a rolling. With a star mark, note down that how to write the kinetic energy of a rolling. You will need these things. Object is moving from one place to other. Half mv square. Meantime, it rotates around itself. Half I omega square. Can you remember? If object is rotating around itself, it has the rotational kinetic energy. What? Rotational kinetic energy. And if object is moving from one place to other, it has the linear kinetic energy. So here in a rolling, you have both components, half mv square plus half I omega square. Half mass times velocity square is the linear kinetic. This velocity is the velocity of center. Velocity of center. To write the linear kinetic, you use the velocity of center. The circumference is a mess. 2v root 2v 0. To write the linear kinetic, half mv square, you use v from the center, velocity of the center, and half I omega square. For the rotations, half, instead of mass, it's moment of inertia of the body. Instead of velocity square, it's the angular velocity square. Note down this thing also. Okay. Then, can you solve the question number 98 and question number 99? Then let's go for the interval. Question number 98 and question number 99. Question number 98 and question number 99. Then we will move to the interval. Okay. Question number 98 and question number 99. I think you all know our results. You might, most probably 99%, 99. You might have seen our results in the social media. So what is the secret behind these results? I'm teaching the theory to the deepest level. If not, you can't earn 100 marks in the paper. We have to learn for the 100 marks value. Okay, to take a pass, we have to learn all the things. If you don't know some theoretical parts, then how can you take 75 marks out of 100? You have to learn for the 100 marks. Then it's easy to defend 75. Okay, remember that. So I'm teaching to the deepest level, not missing a single theory. And we have to solve a lot of questions. In this journey, we will have to do many sacrifices. I haven't given a single holiday in April. I haven't given a single holiday in April. In my life, I haven't given a single holiday in a POA day. I have continued the classes. Why? if we need to learn all the things without missing a single point, and if we need to solve a lot of questions, we need time. So we don't have something called holidays. I haven't given a holiday in a poor day. I haven't given a holiday for the Urdu week. I haven't given a holiday in any case. If I'm well, if I'm continuing the classes. That's how I have created these special results I have gained. Okay, so you have to agree with that if you are willing to work with me. What will you get? You will get the complete theory to the deepest level, and you will get the chance to simplify many questions with me. It will definitely help you to have A plus. So that's the scenario. That's the method that we follow. Okay, let's go to the question number 98 and 99. A rolling means a linear motion combined with the rotational motion. The best example is the vehicle wheel. So first of all, you have to draw the velocity diagram for rotation, tangential and the angular. Then you have to understand the linear components of a velocity when an object is having a linear motion. Then you have to take the vector addition of them. Then you will get the velocity profile for rolling. And from the university first year, without the proof, we can take for the A level V equals R omega equation. You don't need to prove it here in A levels. What's V? Velocity in the center is equal to R times omega while rolling. And how to write kinetic energy? Moving from one place to other, linear kinetic half mv square, angular kinetic half I omega square. Okay. So let's go to question number 98. Let's go to question number 98. Question number 98 and 99. Question number 98. A bicycle wheel has a radius of 0.25 meters. The bicycle wheel has a radius of R, where R is equal to 0.25 meters. And mass of 0.8 kilograms. The moment of inertia is 4 into 10 to the power minus 2 kgm square. Instead of mass in a rotation, you have to use moment of inertia. The wheel rolls without slipping on a horizontal surface, making 7 revolutions per second. It's in a rolling motion. Now you will ask me, sir, in each and every question, do we need to draw the rotational velocities separately and the linear velocities separately and add them and draw the final diagram? Do we need to do that, or can we use the velocities at once? Putha, remember, you can use the velocities at once. You don't need to draw the linear part and the rotational part and show how they combine. You can straight away use the facts. But remember, in a kind of a question, if they ask you to show the diagram, so you have to practice it. But remember, if they are not asking to show it again in a separate diagram, straight away you can use these values. So in a rolling, center of gravity, the center will have a velocity v, while the topmost point having a velocity 2v. This place, v with a perpendicular v will end up a root 2v resultant. And in this part, v, a root 2v resultant. And in the bottommost point, velocity is 0, cancelled out to two sides. And omega is also present. You can use this, straight away you can use this, but if they ask, you should know the method to take it. Okay. Now omega is given 7 rounds per second. 7 revolutions per second. That means 7 rounds per second. 7 rounds per second. Is 7 rounds per second a SI value to SI method to give the angular velocity? No. What do you mean by 7 rounds per second? 7, what is a round? 360 degrees. But that means 25 radians. 7 into 25 radians per second. We have done this earlier, the unit conversions. How the RPM and RPS convert into radians per second. We have done this earlier in the beginning parts. How RPM and RPS is converted to the SI unit. It's rotating 7 rounds, 7 revolutions, 7 rounds per second. Around 25 radians. Okay, so the angular velocity is equal to 14 into 3.14 radians per second. What's the value? 14 into 3.14. 14 into 3.14, 43.96. 44 radians per second. The actual angular velocity from the SI units, 44 radians per second. Then, of the center. The second one, the linear velocity of the center. Equation V equals R omega. Similarly, it's same as the equation that we use in rotational motion. But in rotational motion, the tangential velocity is equal to R times omega. Here the tangents, it's a mess, 2v root 2 0. It's not the case here. In a rolling, the velocity in the center of gravity, velocity is the center, is equal to R times omega. So the linear velocity in the center, R is 0.25 and omega is 44. So the velocity in the center is equal to 11 meters per second. 11 meters per second. What is this? It's the velocity in the center, this V. 11 meters per second. Okay, what's the next thing they ask? Linear velocity of the topmost point. It's 2V. 22 meters per second. Can you remember the velocity profile? If the center is having a velocity of 11 meters per second in a rolling, the topmost point is 2V. What do you mean by that? 22 meters per second. 22 meters per second. Okay. Then total kinetic energy. The total kinetic energy. Kinetic energy is equal to half mv square plus half I omega square. A rolling contains both rotation and the linear parts. Half mv square, half mass 0.8. To write the linear velocity, you have to use the velocity in the center, 11 square. Plus half, in a rotational motion, you use moment of inertia instead mass, 4/100. And angular velocity square, angular velocity 44 in SI units, 44 square. 44 square. Okay. 11 square multiplied by 0.8 divided by 2, 48.4. 48.4 joules from the linear side and from the angular side. 44 square 38.72. 87.12 joules. 87.12 joules. The linear, the total kinetic energy, 87.12 joules. Okay. Finish the question number 99 before the interval. Finish the question number 99 before going to the interval. Question number 99. A disc of mass 5 kg. A disc of mass 5 kg rolls in a horizontal plane. The moment of inertia is 2.5 kgm square. 2.5 kgm square. And the linear speed 2 meters per second. Linear speed is equal to 2 meters per second. And the radius is 1 meter. R is equal to 1. Linear speed. When they say the linear speed, it's the velocity in the center. Vg, in the center of gravity. 2 meters per second. If it is not especially mentioned, it's the velocity in the center. Not in the circumference, because the velocities components in the circumference vary. Sometimes it's 2v on the top. In the right and left side, it's root 2v. So how to say a single value? While the motion carries on, the velocities in the circumference change. It's a special situation. It's a rolling motion. So what happens? If they say the velocity, it's the velocity in the center that they mention. Okay? Okay. So the angular velocity. In a rolling motion, velocity in the center of gravity or the center is equal to r times omega. Velocity in the center is 2. Radius is 1, where omega. Omega is 2 radians per second. Omega is 2 radians per second. Then the total kinetic energy. In a rolling motion, object moves from one place to other, having a linear kinetic energy half mv square and a rotational kinetic energy half I omega square. Half mass is equal to 5, velocity 2 square. Half I, moment of inertia 2.5, omega 2 square. 10 joules plus 5 joules. 15 joules. 15 joules. Okay. Now after the interval, we have to pay our attention to the special scenario where a rolling is happening in an inclined plane. Now the two questions we solved is about a rolling happening in a linear, in a horizontal plane. There's a slight difference. There's a slight difference when it comes to a rolling in a inclined plane. Okay, write the next topic before the interval, then we'll move to the interval. Rolling of a body in an inclined plane. Rolling of a body in an inclined plane. Rolling of a body in an inclined plane. In an inclined plane. It's slightly different. We have to learn it separately. Rolling of a body in an inclined plane. Okay, now. So what's the time we get together? Now it's 9:07. Shall we start at 9:20? Shall we start at 9:20? Okay. As it's the first day, I will give you until 9:25. As it's the first day, I will give you until 9:25. Okay. And I need all of you to be present at 9:25 because I have to start a theory. Okay, you will miss the theory if you get late. Okay, so I have given you plenty of time. Let's start at 9:25. You have 15 minutes. 9 sharply at 9:25 as I have to start the theory. Okay.